1, 2.
Oh.
Yeah, I recognize Dan's voice. Okay, you're there. We could start. So, okay, we are at the top of the hour. So, welcome to this NMOP, Network Management Operations virtual group meeting with a special focus on network anomaly. So this is maybe a virtual meeting, but this is anyway an IETF meeting. So please note well, there are IETF policies, various one. So as a couple of quick reminders, by participating to the IETF, you agree to follow the IETF process and policies. You are aware that any IETF contribution is covered by patents and patent application that are owned or controlled by your sponsor. You must disclose that. And I let you read the rest of the slides with at your convenience. This meeting is being recorded. It's going to be on YouTube later on. While people are reading the slides, do we have any note taker? So this is actually collective meeting minutes. So feel free to update the meeting minutes, part of it or the entire one. So any note taker, and I'm just going to resend the link to the meeting minutes to the chat right now. Okay, so let's all do our best to update the meeting minutes. The point is not to cover what is already covered by the slides, but mostly the interactions and the action items. So we have a compact agenda, which is very interesting for virtual meetings. So it shows the interest that people have in this working group. So this is great. We've got first the agenda bashing introduction with Matt, Mohamed Boukader, co-chair, and myself, Benoit Claes. Then we've got a part one, which is operator inputs, a part two, which is what we're going to deliver and working on in NMOP, and then 15 minutes of discussions, open issues, next steps, etc. So we have the detailed agenda here. As I mentioned, the point number one, Swisscom is going to express the postmortem for network incident. Bell Canada as well. Orange, as a newcomer, will discuss knowledge graph, and INSA Lyon will discuss about anomaly detection in ISP. The part two is the architecture for network anomaly detection framework, the experiment that was done on the network anomaly lifecycle draft, and then the part three was discussion. Any agenda bashing at this point in time? Okay, hearing none. That will be the agenda. In terms of working group documents, so accepted by the working group, this one, the top one, is on the agenda, and we're going to present it. And this is the last slide for the introduction by the chair. So, Matt, what did I miss? What did I say wrong? Feel free to interact.
Yeah, I think that you have said what we wanted to say as an introduction. I think that the floor now is to the operators to really explain, I would say, their needs on the anomaly detection. So I think the floor now is for Thomas for starting part one.
Good. So then, shall I take over the screen? Is that okay?
Yeah, please do so.
I get an error message when I try to share. All the slots for the requested media are already taken.
So Matt, can you share Swisscom slides? Thank you.
You can do it right now, Thomas, on your side.
No, it works. Now you should see my screen. Good. So let me start. So here I would like to share a so-called network analytics network incident postmortem at Swisscom. So the focus will be, I will give in the beginning an introduction, like what exactly happened in terms of the incident and which operational metrics we were collecting from the network, and then also what analytical metrics were we deriving. So basically what network anomaly detection was able to detect, and then go at the very end into the improvements part. Improvements part can be related to the metrics we are collecting from the network, or it can be also on the anomaly detection system as well. And this is a regular exercise we are doing within Swisscom, but also among other operators and vendor itself, because at the end we want to improve and learn from each other. Just to high level describe, so the focus is on anomaly detection. We are looking at the network holistically. So basically the network telemetry framework describes us how we are organizing the metrics from the network. We are collecting IPFix, BMP, and young push metrics, and we are collecting those metrics through a real-time data collection and make those metrics available in a message broker, which is then in real time be consumed by the anomaly detection system. So just to briefly explain, we have layer 3 VPN connectivity services across a segment routing domain. We model from a service intent, the layer 3 VPN in so-called logical connection, which is the VPN, and connection points, which are the VPN endpoints. On each node, so on the provider edge and also on the P nodes, we are exporting BMP and push and IPFix and performing real-time correlation among IPFix and BMP, and the anomaly detection system is then verifying from different angles, and I will go into detail in there, the VPN connectivity service. I'm going now in the part explaining first on the right-hand side what happened within Swisscom, and on the left-hand side, this is just a high-level picture to show what the network anomaly detection system has been observed during the incident, during the maintenance window. So on August 14th, there was a maintenance window between midnight and 1 a.m. and there were several configuration steps being performed, in total 15. These configuration steps involved changes in the ISIS overlay bit on the ABR, so offloading the ABR in the forwarding, so that maintenance work on the ABR could be done, and the maintenance work was a configuration change from ISIS level 1, level 2 to level 2, level 3 distribution. And there were also configuration changes on the PE nodes attached to the ABR, where the link between the PE nodes and the ABR were changed from a layer 1 from a level 1 to a level 2 ISIS adjacency. On top of that, since this is an SRv6 domain and we wanted to ensure that the the redundancy of the network is not affected. The so-called locator summarization has been removed and then reapplied at the end of the maintenance window. Throughout the maintenance window, in the overlay, topology changes, traffic volume, flow count changes, and also forwarding plane drops, and also customer data plane DCP congestion were measured, observed, but not alerted. In the SRv6 underlay, we observed forwarding plane drops, but also there they were not alerted. While during that night, Network Operations Center, which is responsible for the 7x24 monitoring of our network, was alerted, and it was alerted due to 2 different applications which no longer had connectivity within the network. One application was related to voice over IP service, while the other application is related to the mobile subscriber control plane provisioning. So basically the relationship on what connectivity service a mobile subscriber, what bandwidth a mobile subscriber is receiving. Even though both application notified that there was a problem, the involved platform teams who are responsible for those applications did not find the causality, the reason why the application connectivity was interfered. And shortly before 2 a.m., basically the maintenance window on the core network where the ISIS changes were being done in the overlay were finished, and the team concluded that there was no connectivity service impact observed during the maintenance window. Then later in the morning, during the day, the Network Operations Center was being contacted by those application teams again, and they wanted to find out whether the reason for the connectivity impact has already been found. And a little bit later, through the researching on what kind of things in the network has changed, the Network Operations Center concluded that most likely the impact on those applications were due to the configuration changes in the SRv6 core. And shortly after, we started the post-mortem maintenance process, where we start investigating the causality, looking at from a network analytics perspective. So what you can see on the left-hand side, the output from network anomaly detection is we have a so-called overall concern score. So this is a weighted score over all the different checks which are being performed. And the output you're seeing on the screen is for a limited amount of VPNs which are traversing that SRv6 core. So in total, we are looking at 17 different VPNs. And there is a group by for each VPN, so each color basically represents a different VPN. So we observed some so-called flow count spikes. So flow count spikes usually are happening due to congestion. We have a concern in the amount of traffic being forwarded. So usually that's a comparison to the historical data. So we see we were not forwarding the same amount of traffic as usual. And then we have so-called updates and withdrawals in the overlay topology. That hints that there was some topology changes in the network. And we saw also some so-called interface state changes on interfaces related to this connectivity service. In the forwarding plane, we saw some drops, so that the packets are actively being dropped, and we also know the drop reasons behind it. And throughout the maintenance window, there were no state changes in the BGP peerings being observed. Now, here I'm just giving a rough overview about the IPFix, BMP, and YAML push capability we have in the network, and I want to highlight a little bit that a lot of the activities or a lot of the protocols involved in here over the last, I would say, 5-6 years in an IETF, in a vendor context, we brought improvements in, especially in the area of SRv6, because SRv6 is relatively new to Swisscom. We have past experience with MPLS networks, and we want to make sure that the transitions from MPLS to SRv6 works the way how we want it, and we can properly monitor. The so-called applied and operational refers to this so-called pyramid of technology. So this is basically how innovation is being observed in the society and accepted by our network engineers. We understood from the post-mortem analysis that this was not the first maintenance window where this impact has been observed. So I'm showing there were in total 4 maintenance windows on August 6, 7, 13, and 14. And I'm showing here the anomaly detection results from the 2 maintenance windows on August 6th and 7th. The 4 maintenance windows were exactly the same, but were be applied on different locations within the network. The last maintenance window on August 14th was also the one where a location was affected, was the maintenance window was performed where the most customers and the most traffic are being measured, and therefore the impact was the biggest. Here I'm giving an example on operational metrics. So this is flow aggregation, so the correlation between IPFix and PMP. We are filtering on the connectivity identifier, and we are filtering also on layer 4 properties so that we can identify specifically the application, but also in this case the TCP resets. So basically a way of detecting the congestion in the network towards this application. On the right-hand side down, this is the consequence that the network element who provisions the connectivity service towards the mobile customer was no longer able to obtain the information through LDAP from the database, and therefore had to provision so-called fallback services. Here, another example on an application, and both applications, by the way, were had like the alerts which I was mentioning at the beginning. Here, the focus is on a different VPN. I'm filtering on voice over IP control plane traffic, and we can see here at one point in time there were retransmissions happening to do the black holing, the dropping of the packets. Here, another view from in the overlay on the BGP control plane changes in the topology. I'm filtering specifically on a particular route distinguisher, on a particular berth in the network. I'm looking at the so-called local RIP and the changes in the local RIP measured by a BMP route monitoring. I'm looking, I'm grouping over time, over node, and the kind of changes, whether it was update and withdrawal. And we can see throughout the maintenance window, we had primarily updates, and the very last on 057, 58, there was convergence between where prefixes have been withdrawn and then re-updated again. Now here are the operational metrics for a particular layer 3 VPN. On the top left, and let me get the pointer here, on the top left side, we have the topology change in the BGP overlay, the updates and withdrawals. While on the right-hand side, we have the amount of forwarded traffic on the layer 3 VPN throughout the core compared to the previous week. So we can see that we are not forwarding the same amount of traffic than before. The below graph shows exactly the same. Instead of the measured packets, we are looking at the so-called flow count, the amount of layer 4 transport sessions in the layer 4 and the layer 3 VPN. And here on the left-hand side, the amount of drops, forwarding drops observed on that layer 3 VPN. So while these 4 graphs are focusing on the overlay metrics, I have also below added the underlay forwarding plane metrics. So here on the right-hand side, we see on the provider data plane from which PE node to which PE node and VRF, so SIT, the traffic is being forwarded. And here the group by node. So basically we can observe the traffic shift due to the redundancy changes in the core. And throughout that, you should see like in which redundancy state changes, which impact in the network is happening. This is the view from the metrics we are collecting from the network and how manually you can query the data and visualize and dashboard the data. Now I'm switching, and basically anomaly detection does very much similar check, but in an automated fashion. So here you see the overall concerning score, especially the concerning score goes up when many things in the network changes at the same time. So we see here that there were topology changes, and those topology changes were leading into forwarding plane drops. While at the point where there were flow count spikes, so basically congestion being observed, we are more conservative on the overall concern scoring. So looking at the overall score, we see that basically 4 out of 6 checks in this case have been applied. We are also very much pleased with the auto profiling, how the outliers were being detected in this case. Going to a different VPN, similar view here, also topology changes, some drops. Here we see clearly where retransmissions are happening, so the amount of traffic, the amount of flows, layer 4 transport sessions were going spike-wise up. And we can also see here that basically that traffic volume was changed in the core due to the retransmissions. And again, we can see in this case, more PE nodes, more WRFs were involved in the overall forwarding throughout. So the more tunnels were happening in the SRv6 domain. Also note that the amount of traffic here is much more lower, so it's a different characteristic. Now, looking on the anomaly detection side, what we have been observed, you see from the scoring that the values are relatively low. That's due to the auto profiling currently missing. We are still for the real-time streaming version with the development still not finalized there. So currently we have like 2 versions of the system. One more on a limited POC scope where we have the full feature set, while the real-time streaming version covering all the layer 3 VPNs, which is currently around 13,000 VPNs, but some of the features like auto profiling are missing currently. And due to that auto profiling, the scores are not that high. That's one reason. And we see, but from an observation perspective, we noticed the withdrawals, we noticed the drops, and also some of the missing traffic, and we were slightly elevating the overall concern scoring. Now, important aspect is also that having such a system not only in a production environment, but also in a lab environment. Unfortunately, of course, our engineers were concerned about the observations in the production network, therefore went back in the lab environment and tried to reproduce the problem. These are the metrics, and we are using the exactly same dashboarding, exactly same queries as in the production network now in a lab environment. And we were able to reproduce the problem in the lab environment, and even were able to identify one of the reasons, one of a configuration item which led to that connectivity service impact. Now, there is a long list of what went well and what could be improved. I think I'm just highlighting a couple of things which I believe is important. One is basically the time after the metric was observed in the network versus being alerted. We are here now in the range of 120 to 180 seconds. This is basically the delay mostly relates to the delay of the so-called flow aggregation. So since aggregation means also delaying metrics, but then compressing the amount of metrics, allows us basically to save compute power on our side, but has of course a negative impact on the real timeliness. However, we are very pleased with this 120 to 180 seconds, especially after the migration to this real-time streaming-based anomaly detection system. Another important observation is we knew from the past that migrating from MPLS to MPLS SR, it's important not only to monitor the edges, but also the core devices. However, we knew that when we are moving towards SRv6, in order to cover the forwarding plane and the control plane, that's a lot of innovation needs to be done in a very short period of time. And we were focusing on the forwarding plane only, and we did not cover the control plane. And here we see clearly we succeeded on the forwarding plane side. However, we are missing the visibility into ISI's control plane. Currently today, visibility into the ISI's control plane is best established through redistribution in BGP link state and then exporting the information through BMP locrypt. Notably, there are also 2 IETF proposals in the past, which did not find much feedback from the operators and vendors to expose the IGP LSDB directly, which has, of course, especially in SRv6, the advantage that not all the SRv6 attributes needs to be supported by BGP LS. We would have direct access to the IGP LSDB. Another, I would say, important aspect would have been that there was questioning whether we had forwarding plane loops. Since we have now just in the forwarding plane a so-called statistical view, we are not able to see how each packet is being forwarded node by node throughout the network. What's missing is the forwarding plane path visibility. So per RFC 7799, that's passive hybrid type 1. And I would say maybe last but not least, also the transaction ID in netconf could have helped to correlate the exact commits, the configuration changes on the network with the topology changes and the forwarding plane drops. That's it. Any questions or comments on the? I see we are almost top of the hour.
Thank you, Thomas. Yes, you've got 1 small minute for question, comments, feedback. Rob.
So just a quick question on the passive hybrid. How would you know which packets to actually target for that information? Because presumably you wouldn't instrument all the packets. So how do you know which flows are being dropped to then say I want to be able to see these flows to work out where they're being dropped? Is there a solution for that, or am I missing something obvious?
Yeah. So basically, our wish is basically yes, we don't want to basically measure all the packets. Today we have a sampler where we say randomly which packets we are selecting. In the future, we want that the matching criteria for which packets to be selected should be related to the quality of service concept. So some packets are more important than others. Therefore, on packets in the priority queue, we want finer grained resolution, while on the best effort parts, sampling is perfectly fine.
Okay, so is the answer sort of statistical sampling ultimately? Okay.
Right.
Thank you.
Thank you. Thank you very much, Thomas. Very interesting. always great to hear from operator at the IETF and their requirements. So Dan, you're next with the Bell's journey to the mountain.
Yeah. Do I control the slide myself, or how do I do that?
Yeah, you can do it right now.
Okay. Well, I have to tell you next slide. You're gonna move it.
No.
Yourself,
You have already the control, Dan.
I'm not sure where is the control.
You should see 2 arrows left and right at the bottom of the screen.
Meg, I think you have given control to the wrong Daniel.
You have to give me more control.
You have given to Daniel Bernier instead of Danwer.
Oh, you gave it to Dan Bernier instead of me. Benoit, are you able to change that? Ah, there you go. Ah, nice. Okay. You guys still hear me?
Yes.
Okay, good. All right, so first, I have to admit, I'm super nervous to do this presentation. It's on, revealing outages and stuff. Heartbeat is 60. Usually it's 55 for me. And just before this call, I had a call with my director of the NOC to get blessing, but also mutually boost our confidence to expose this to the world. So I hope it's going to be a good experience for you guys on your side. I'm going to go over what we started doing in regards of the RFP 9232 and the few steps that we took. And then I will cover a few outages that we encountered. So our very first journey for us started for RC 9232 in last year, in summer last year. We started with exploration lab in August, and then we went straight to production in a pilot in December. By December, it was kind of completed with few devices. And then we went to extend this pilot into production with more devices in April. And as of now, we have about 100 devices-ish in our platform. And so far, one of the experience that it provoked inside our organization is a real change of mindset in terms of centralizing information, the way we gathering the IP fix, the BMP, and then the pseudo and push all together. I did 3 different feeds for telemetry. This is new. The analytics, the make sure that every domain centralize their data and also growing their formalizing their standardizing, follow the same recipe is a mindset change for us so far in this experience. The strategizing or centralizing the data to get more out of the whole backbone is also something new, because at Val we can claim we're one of the oldest telcos, which means we have lots of legacy systems over the last 50 something years, and we just like other telcos, we're not really good in evergreening everything and keeping up top notch. So the information is in different inventory systems. So we're coming out from this era, but also in going in those new ways. In my quadrant where I have the info from multi-vendor, it's not the same from one vendor to another, the standardization, the data. And even within a vendor, different platforms are not really the same, how we stream the data and how we receive the data and the quality of the data. That is something that is real obstacles in counting of this working group to help us out there. Telemetry and the quality. So the quality, ideally, you'd like to have the normalization and the standardization of the data out the router or the node itself, not wait too long in the stack of software to add other layers in your stack or your anomaly to re-standardize it after. So those are the things that we really struggle. But we are not alone in this world. So you probably see or saw in the news a year ago when BAL and Swisscom created a partnership. We created an MOU and we decided we're going to work together to overcome these obstacles, and we're going to share experience, we're going to share outages, we're going to share hints, and that was really something that eye-opening on both sides, I would say. Maybe Thomas in the question could also comment on both sides of BAL and Swisscom, and I know other operators would like to join. But here we wanted to have the executive to agree that we're going to do this and we're going to get together to push the industry to standardize protocols and the overall telemetry. So now I'm going into the one example of an outage that we had. This one, the beginning of this of the year. I'm picking this special outage. You'll see there's something special around this one. But in this case, we had like a BNG prime going down, and the backup, the BNG did not pick up. You will hear me a few times mentioning that we're really fast in detecting when something goes down. And I say that in the sense like over the last 30 years is one thing we know is when something goes down in a minute, we know. We don't really know or aware of the correlation or what it means from the customer perspective. Is it do we care? Do we not care? How many are dropped? What services are in fact affected and impacted? And this is what we get with those telemetry streaming that we've been talking, like the Yang push, the IP fix, and the BMP, and so on. But without that, we are really much in blind. The correlation doesn't really come up automatically, and that's what we're trying to solve. Now, the reason why I picked this outage, in this case here, I wanted to hide. The point was not to put the spot on the vendor. We have many different outages of this ones. We can from different vendor. In this case, that was related to the software, not just the connectivity. So if I move on, as I mentioned earlier partnership with Swisscom. We had the exact same. We observed same outage on the Swisscom side. BNG prime down, back up, did not pick up. The little picture here is just a way to say we're drinking from the same cup. We're comparing operator to operator, our operational experience, and how we get around these things. So Swisscom and sometimes us, we host calls where we do share these type of information, and we try to enhance whatever protocols, streaming protocols that needs to be enhanced to have a better quality in terms of data. Those are the points that Thomas just touched before. So these two, the previous one and that one, was the exact same outage. But in our case, we're not as advanced as Thomas and his team are, so we're just getting started. So we are still troubleshooting and finding root cause the traditional way for this part of the network. Now this outage, and I hope you appreciate my new acronym here, because I could keep adding many other outages as we're building our confidence to talk about outages. This one is kind of, I would say, the mother of all type of outage. And precisely, this one is between central and east, a few east of the country in Canada. A few links went down over a period of time, not in one shot. So 2 links went down. One was disconnected because something needed to be repaired. And then over time, we lost like 5 links out of 6. And many customer impact again. The link that was still up means that some customers were able to keep working, but in degradation mode. So we have like a view or an idea that the 4K stream will be blurry a little bit. People will lose packet, and their session will not be working as it should. And many other customers, let's say the mobility side, literally down in this case. So once again, what we knew is when links goes down, that we know pretty fast. We don't know the chorology or the correlation, or what does that mean when all those links are down? Why didn't we reacted when there was 3 links that were still up? How did we know? How can we know before what will happen from a customer side? And in this type of design, like I mentioned, well, very old, lots of information is memorized in some key players. So it's not all centralized and known. And because of that, then when these things happen, there's many calls that are being done between groups and teams. People are trying to figure out who has the latest and the greatest and what is happening. And we're wasting time to bring back the service. Most of the time, we would be between either reload the router, but make sure you have all the information so the vendor knows what to do to patch it if it's a software problem. In other case, where are the other links buried in ground that we could pick up to reconnect and bring back the service online? So our objective would be really to determine the root cause or the impact of this type of outage in minutes or even in seconds, ideally, and bring an automatic way to bring a correlation with the customer service. So we know before the customer call what exactly is happening, what's the root cause, and then we can provide like a delay. It's going to get back in service in X amount of time because we actually know what's happening. And usually your reaction time is about 7-8 minutes for that. At the moment the outage happens, 7-8 minutes, you need to know these things. If I move to, so the main objective of what we're trying to do when we collect that much data centralized is really able to accelerate and emphasize on anomaly detection in real time. Is also to have a really good view of the network layers, the topology layer. It's also very useful to optimize even better. So we don't know, maybe there's a couple packets that are lost here and there once a week, and it's always happened between 10 a.m. and 11 a.m., and it's not really optimized at that moment. That is the bug we could, usually people will take months to find out and try to fix because the information is very dispersed and pretty much all over the place. We're really trying to accelerate the troubleshooting and bring solutions very, very fast. So the key is almost, you need to know what's happening on the customer side, what's their impact. Maybe it's okay, there's a couple packets that are being dropped, there's absolutely zero impact on the customer side. And then you need to be very fast to provide a solution and then fix it. And that's something that it's kind of it's an art. How do we do that across many links, many nodes, many endpoints, and many branch offices and many homes from a customer side? I am pretty much done. Now I will invite other people to get out of their comfort zone and talk about your outages. How is it for you? I have a pretty good idea we're not the only one in this state from an outage perspective. I'll open for questions.
Thank you very much, Dan. We like it whenever our operators present IETF, but thank you very much for being candid about outages, because that's going to help us improve. Rob,
Yes,
you're in the queue.
Thank you.
Yes, just a quick question, Dan. So you're talking about obviously trying to make use of, you're collecting all this data and trying to make use of it, and you're saying that's obviously a difficult thing to do. Is it the difficulty there is trying to know what the right data is to collect? Is it the issue that the data that you need isn't being exported from the devices? Is it there's too much data and too much noise, or is it too early to know which of those things it might be, or it might be a combination of all three of them?
It's a combination, unfortunately. I'd like to give you something very, very precise as a problem statement to work on. But you see, with the NOC director earlier this morning, we were talking standardizing the network design itself. Like, for example, in central Canada, most of the fiber is underground, so fiber cut is not really a problem, but on the east, it's not. So network design standardization is one thing. That's nothing to do with telemetry. But as soon as you go with telemetry to be very accurate, so imagine if you push it to, say, closed loop automation one day, where human is not involved. So the system will only have the data to analyze and react and go make a change in the field. So the standardization in the node itself between vendors and between platform of the same vendors become key, and the richness of the data to be crunched or parsed in the system also becomes key, right? So, hoping I'm answering your question.
Yes, thank you.
Thank you, Dan. So the next one is yet an operator, Orange this time, talking about knowledge graph. So Lionel, the floor is yours.
Okay, thanks. Hello, everyone. My name is Lionel Teada, and I am a research engineer working at Orange, International Network Infrastructure and Service Provider. And before we begin, I would like to first thank the chairs of NMOP for their interest in my work, as their encouragement to participate in this working group. Indeed, I have been working on knowledge graph-based framework for anomaly detection and incident management in large-scale ICT systems for many years. And it seems that the ideas I developed during that time may resonate with this group. So I recently took it upon myself to formalize these ideas by writing them down in an internet draft, and to which I gave this fantastic or utopian title, depending on your perspective, knowledge graphs for enhanced cross-operator incident management and network design. I hope you'll find this an interesting roadmap. So let's say we have a knowledge graph such as the one shown here. It shows a network topology with a server node at the center for which an integrity violation alarm has been logged. This is on the bottom of the graph. It also shows on the right side a trouble ticket node saying that there is an issue of the packet loss category and that the issue has been reported as related to the server. Please note that this diagram is not just a thought exercise, but it has been tested through some of my work, and it is currently under deployment at Orange at the company scale. However, I will remain at an abstract level in this presentation, if you agree on that, in order to generalize. So back to my fantastic title, the goal is to learn incident signatures and remediation procedures and be able to share them. So to build the knowledge graph, we can see it as a digital map, thinking of the digital map concept developed by Olga Havel in another internet draft, and a digital map that is combined with operational data and operational support system data. But further, thinking of legacy information and network deployment systems, we can leverage young-based configuration data that can be converted to build the digital map, and thereby it will be connecting the decision support systems with the network production itself. But there's still a question, is how can we integrate these different data facets while ensuring the stability of the interpretation layer provided by the knowledge graph, and further, without disrupting the habits related to the low-level tools we use for network deployment. So again, can we have a comprehensive and integrated view of ICT systems for anomaly detection, decision support, and decision support? And spoiler alert, yes, but it will involve making design choices and additional work. Indeed, what we can start from is the concept of digital map. That is an interesting basis to describe and operate networks, but also young configurations that can be converted to build a digital map, notably if we consider knowledge graph. So how do we do that? The combination of these two, the digital map and the young conf, will yield to some proto IT service management knowledge graph, or ITSM knowledge graph in short, as I show in the middle of the two first sentences. But having a knowledge graph means that it is structured by an adequate ontology, or onto ITSM on the upper right side. And this is yet to be discussed. So considering the data and knowledge we have at hand, two design strategies for knowledge graph construction appears. The first one that I have called young KG semantic equivalence, which is akin to say, I have some configuration data. Let's just implement data transformation rules to make a graph out of it. And there is a second one that I have called young KG semantic generalization, which is akin to say, I have many data models, or young models, let's say. Let's make a network of ontology to bring them all together, and the data transformation rules will follow. The ones that can be seen as a policy for the knowledge graph construction functional block here. So in what follows, I'll be focusing mostly on the second use case, that is the semantic generalization. Sorry if I advocate too much, but I'll now briefly explain why. So firstly, the sharing of information involved a public ontology satisfying all stakeholders. And this could not be the case with a semantic equivalence strategy, as there is no ontology at all, or very user-specific, if any. And for the second case, just translating young models to some ontology is nice, but yet it is insufficient, as the related configuration data, which is akin to a digital map, is not sufficient to compute behavioral models. So therefore, we shall need a recontextualization of the translated young models into some higher level ontology, hence the semantic generalization name of the strategy. So now, to get more concrete and join our efforts, here is an experimental plan, or roadmap, if you prefer, that we could use as a basis. It is made of 6 use cases that can be materialized as a modular data processing pipeline for the young KJ semantic generalization strategy. So let's start from the end with a knowledge graph that is made of entities coming from both the young configuration data, but that should be seen through some abstraction layer. That is the ITSM knowledge graph. And to materialize the configuration knowledge graph means to be able to both have a young related ontology, the let's say I will call this, well, it will be the set of young model transformed into RDFS ontologies. And this means to be able, which is trivial, to have access to the young configuration, but at the same time to have all these young data models translated into some set of ontologies. So this means running all these sub-use cases to be able to instantiate some young configuration into a configuration knowledge graph that we can query through the set of ontologies related to young models. And this is important to note that just doing so, having this set of young models translated into a set of RDFS ontologies, enable us to have some knowledge graph of the configuration that we might not want to share the knowledge graph itself, as it may contain private data, but we can already reason through ontologies to extract let's say network topology models and share them because we look at them through an abstraction level. But as we also need to be able to query the graph independently of the underlying young models, we need to implement some meta-ontology, the one that governs the ITSM knowledge graph. And for this, we need to implement some meta-ontology, which is the set of all the young models plus a meta-ontology. But we need to link the two sets, the ontology meta, with all the corpus of the ontology young model. And for this, we need to implement a corpus of alignments between the two vocabularies, the two sets of vocabularies. So, wrapping things up, I wish to address the problem of building an ITSM knowledge graph that uses young-based configuration data while abstracting network details for learning and sharing behavioral models. And for this, the proposed approach is using knowledge representation based on semantic web technologies first. Secondly, it's about the generalization of young models for configuration data, but also to add an extended digital map combining configuration data with operational data and operational support systems data. And this means having a meta-ontology and linking between this meta-ontology and sub-ontologies consisting of young models translated into semantic web ontologies. And overall, well, the natural next step that will be nice for us to join our efforts on will be to experiment based on the proposed use case or on the roadmap I have shown in the slide before. So thank you for your attention. I am all yours for the discussion.
Thank you very much, Lionel. Any question, feedback? Rob?
I feel like I'm asking all the questions, but I've got one for you as well, Lionel. So I was just curious, what modeling language are you using to sort of build the ontology or the sort of relationship between the Yang-based configuration data and your knowledge graph of the network? Is that semantic web related stuff, or is this some other language?
this is only semantic web related stuff. The ontology itself now, you may reach the one I have implemented and shared in open source that is called Noria-O, Noria-O. It is using semantic web technologies, so RDFS all. And for the mapping rules, I mostly use RML, RDF mapping language. This is all public. I have shared them also through Noria-O. And I have some colleagues of I working on automated translation of young data models to ontologies. So that's why I also said we have stuff to share and to move forward on this roadmap. So
yeah, it'd be really interesting to understand. Sorry, it'd be really interesting to understand how well that mapping's working, and if you hit lots of issues, or you can work around those, or there's corner cases that don't work so well. So it'd be good to understand how well you can model the different semantics through.
So let's talk after this. I have currently 2 papers, research papers that have been published and that show how to do knowledge graph construction for a large number of data sources from Orange, including network topology, monitoring systems, organization, and so on. And I have not yet anything to share about young configuration to knowledge graph, but this is ongoing work, and I'm sure we all want to move forward on that. So this is why I'll call for an experiment altogether based on this first insight.
Okay, thank you.
All right, good. Thomas?
Yeah, Thomas Graf from Swisscom. Thanks a lot, Lionel. Just one question, so just for clarification, did I understand correctly that basically the control plane, forwarding plane, and management plane data would be represented in the Yang data models, and then the relationship among the different network planes would come from the IETF network Yang, from the digital map, and you would use basically the digital map for your knowledge graph to establish the relationship among these different planes.
Yeah, that's a good summary of it. Yeah.
Good, thanks.
You're welcome.
Thank you. Anything else? Okay, good. Thank you, Lionel. The next one is the one from INSA Lyon with Alex.
Yeah. So yeah, hello to everyone. I am Alex from INSA Lyon, and I am presenting a work which has been done between NII, Swisscom, INSA, and PMSCCT, which is a platform to detect anomalies in internet service provider. So first, I will present a bit of the context of this project, the main architectural components, and I will present 2 use cases to show a bit how from the data can we detect these anomalies, and I will end with a project status and a conclusion. So first, monitor networks for an internet service provider is important to minimize service impact. Issues happens to all the networks, but what it matters is how a service provider manage those interruptions. These interruptions cost you money, but also make you look bad when you make the news. So in this project, what we want to do is investigate how can we detect anomalies in a real-world internet service provider. Which data can we use to detect these anomalies? Can we base a platform only on standards? And if can a rule-based approach be effective effective rather than dumping all the data to a machine learning algorithm. This work is an extension to the work that was presented 1 year ago, and also actually during the postmortem analysis from Thomas, which we implemented a rule-based anomaly detection for BGP and PLS VPN environments. And the idea there was so classifying all the customer VPNs to customer profiles, and for each customer profile, propose strategies that were composed of a rule-based checks. And these checks were based on interviews with the network operator and based on what they do on their daily job. So, for example, comparing the traffic to last week, checking if there are spikes in control plane or a status of an interface. And this is a platform, as Thomas showed already, that is currently deployed in Swisscom for L3 VPN customer connectivity services. The idea is pretty simple. What we want to do in this platform is mimic what an operator does when looking at the data. So, for example, if they see that there are some traffic counters that are being alarming, so they get a bit concerned, not too much. If at the same time they see that there are some prefixes from the same customer that are withdrawn, they are getting a bit more concerned. And lastly, if they also see from management plane that there is an interface going down, they are pretty sure that there is an anomaly. And what we do is implementing all these sometimes small checks that these operators do on their daily basis, aggregate what we call concern scores, which are the results of executing these checks, and alerting the NOC if there is an issue. And the idea here is we have done already on the VPN platforms, and what we want now is proposing strategies, implement specific strategies for monitoring autonomous systems traversing our internet service provider. On the VPN side, the VPN was identified by BGP communities, and in this use case for internet, what we want to monitor is autonomous systems. We have a few categories which we are focusing right now. First, disruptions. These are events that break the connectivity services, such as losing a top talker from the internet, a neighbor peer that has been disconnected from the internet, or even performing trending analysis, always saturating a link with a neighbor peer. Secondly, we have anomalies. These are events that do not break the connectivity services, but they impact the business of an ISP. So, for example, traffic that goes from a ZMIN3 peer that has been moved to a transit provider, and therefore we are paying for those packets. Monitoring traffic ratios on ZMIN3 peers. Maybe we want to renegotiate our peering agreement. And then as a last category, but for us at least is low priority, is security-related anomalies such as prefix hijacks or DDoS. We are more focused on, at least now, on operational anomalies. The architecture, what we are doing is getting telemetry data from the network, forwarding plane using IPFix, control plane using BGP and VMP, and management plane with YangPush. We are collecting this information with our collector, PMHCT, who decodes these messages, but also correlates the data and enrich the data before pushing it to Kafka. And we ingest at the end of the Kafka to our time series database, which we are using Apache Druid. And we, as a rule-based anomaly detection, we are pulling this database to perform these checks and generate these concern scores and alerts when there is one. What type of checks have we implemented so far? So from IPFix, we are comparing the total amount of packets and bytes to 1 week before, but also comparing the slope to check for tragic loss of packets. And then spikes in flow counts, spikes in drop counters, in control plane detecting spikes on withdrawals, updates, or even peer down sessions, and in jump push, detecting that an interface has changed from up to down. As I said, these are based on interviews with the operator and also on post-mortem analysis, such as the one that Thomas and Dan has presented. And during those, we are getting feedback from them how we should detect all and implement all these rules. I will now present 2 use cases just to get a bit the hands dirty. So in this case, what we want to detect is that we have lost a top talker. A top talker is an IS that sends most of the traffic to you. And from our collector, what we receive is different flows from IPFix that are correlated to the AS path. So we have the AS path that is correlated to the destination IP address, but also the AS path that is correlated to the source IP address. And first, in this case, what we need to compute is the top talkers from our network. And in this case, is aggregating all the traffic that comes from an origin AS, which is the last value of the AS path, in this case, the AS path source. Once we have these top N top talkers, let's say, we can monitor and implement a strategy, which in this case, based on experiences comparing ingress traffic, so traffic coming from the top talker to us to last week, checking also the slope, spike on egress traffic on the flow counts, and then, of course, withdrawals and updates. This strategy is based on past experience, and is based on the incident that happened in 2021 from Facebook, where from Swisscom side, they saw first a bunch of BGP updates and withdrawals, but from the traffic side, we see 2 different patterns. One pattern, traffic that goes from Swisscom to Facebook, we see a spike. These are applications that were trying to actually to reconnect to Facebook servers, but also on the other side, traffic that goes from Facebook to Swisscom customers. We also see the traffic that has gone totally down. And what we do is, after this post-mortem analysis, implement what they feel that is important when detecting an anomaly. And then a second case is detecting traffic that goes from setting-free peers to a transit provider. In this case, it is not a disruption, it is an anomaly, since there has not the connectivity is not broken between our customers and the destination AS. But from autonomous system, we are losing money because this traffic, we are paying for it, and therefore we want to detect it. And for this, we are leveraging the BGP communities. What internet service providers tend to tag their peers with a community. That means if it is a provider or it is a settlement free peer or a customer. And what we do is aggregating this traffic based on these communities to see first how much data is coming from a settlement-free peer, and secondly, how much traffic is coming from a transit provider. And secondly, we can track the ratio over time and an alert when there is a big shift of traffic to check if there is an issue on our network or it was actually the customer who wanted this shift and therefore we cannot do anything. But at least we want to be alerted in case of there is an issue in our network and we are paying the bills a bit more expensive. So this project started 1 year ago. We are still on a preliminary phase. We are collecting IPFix and BGP from the network. In the lab, we have also VMP and YangPush. And right now we are implementing all these strategies in Python on a pooling-based mode and conducting tests in the lab in Swisscom and analyzing the production network. The goal at the end, as we did in the VPN use case, is deploying this platform for internet for a subset of autonomous system first. And then just to conclude, network operators, they want to be alerted when there are issues, but they also want to understand why they are alerted. So that's why we are providing a solution that first, it's based on IETF standards and open source solution, but also based on the feedback and what they do daily so that they get what's the issue when they are alerted. And what's next? So we are planning to complete the use cases, designing them, but also implementing them so that we can test in the lab. Another goal of this project is also detecting missing gaps that could support anomaly detection for service providers. Maybe in some use cases, we might need external views, such as root views, and maybe in the future, root cause analysis. And then just for reference, so this work has been presented in IEEE norms in this paper. So anyone interested can go on that paper, and the second paper is on the VPN networks. So thank you very much, and I am open for questions if there are any.
Thank you, Alex. We've got 1 minute for questions, feedback. Okay, here are none. Thank you again. So the next presentation is with One Thing and Pierre on our working group document, the architecture for network anomaly detection framework.
Hello everyone. Can you hear me well? I think yes. Okay, so I'm One Thing. I'm presenting today on behalf of the co-author of the draft Network Anomaly Architecture, the Pierre-François and Thomas Graf. So during the last IETF, we presented this new draft, which is a proposal for the architecture for network anomaly detection framework. And we focused last time on the motivation of this draft and also the relationship with other relevant drafts, which involves network anomaly semantics and network anomalies lifecycle. And in today's session, I would like to recap a little bit what we discussed last time and give you an overview of the current status of the draft and some open issues and feedback and next step we're going to take before the next IETF. So to recap a little bit the draft itself, the motivation. So first, our motivation was to define a generic and extensible architecture for a network anomaly detection framework to ease the comparison, the exchange between different network anomaly detection systems, because nowadays we have tons of network anomaly detection system, and that can be very different. However, whether they are knowledge-based or AI-based, we still see a lot of common points. So we aim to extract such common components and build up a common architecture from high level to put all the different systems on the same level. So people are speaking the same language to further ease the exchange, the comparison, and integration of different systems. And ultimately, we can achieve a better precision of the network anomaly detection. Also, this draft anchors two different drafts listed here. The network anomaly semantic, which we define the semantic metadata annotation to help to validate, to test the different network anomaly detection, and also enables data exchange between different parties in a standardized way. And then the second is the anomaly lifecycle document that where we describe this lifecycle process to iteratively improve the network anomaly detection system accurately. And in terms of the implementation, we've already started to describe some applications that are conforming to the architecture, and also will be along with some open source running code in the future. Okay. One thing to outline is we are not talking about general anomaly detection. We are talking about network-specific anomaly detection. So what does it mean? It means we are constantly monitoring and detecting any network or device topology change from 3 different network planes, which is forwarding plane, control plane, and management plane, and indicates whether those change might negatively impact the connectivity service we provide. So to achieve this objective, we extract those common components and build such an architecture due to the limit of time. I think I will not go into detail to each component here, but we can go through this architecture from the source to the end to see some main components. At first, we can divide those different elements into 4 phases, in my opinion. So the first phase is the data collection and the data processing phase. Inside that, you have the network telemetry data collection, and which and also those raw data will be sent to the message broker for the real-time streaming needs. After that, you have data aggregation processing and also network modeling. Once we have the processed data, it also goes to the long-term data storage for the further usage. And the second phase will be the anomaly detection phase. So once we have those processed data ready to do some anomaly detection on it, we have those service interruption detection, which we detect individual anomaly from different angles, from different dimensions. Also, we call this individual anomaly symptoms. And once I have different symptoms, we have the alert aggregation part, which correlates all this relevant symptom into one single alert, and further send forward to the message broker and to the alert and problem management systems in the end. And the third phase, I call it refining phase or learning phase. You have post-mortem system, data profiling, and machine learning. They are all playing a role of fine-tuning the current the algorithm of anomaly detection. Last but not least is the replaying. Replaying function is crucial for any network anomaly detection system to be able to validate refined anomaly detections algorithm and be able to exchange between different systems. So in terms of the current status, so this document is a reference document to anchor different anomaly detection work items. Also, recently this draft has been adopted by the NMOP working group. And also we got quite a lot of feedback from the last IETF. They are mostly about the optimization of document structure, also some suggestion for the terminology consolidation, such as we were suggest to consolidate the service and customer terminology in the draft, and also to refer to this terminology of symptom inside the draft. Other than that, also have some suggestion of reference here. We suggest to refer to those listed drafts. We will be looking into them and decide whether they are relevant or not. Well, so for the next step, it will be, of course, we're going to be taking care of the comments, including upcoming comments, and to update the draft to address those comments accordingly. Well, thanks for your time. If you have any question.
All right. Thank you, Wanting.
Thank you.
So I see from the agenda it's you and Pierre. So is there a second part to this, or?
No, I think he cannot join today, so I'm just presenting.
All right. Very good. Just double checking. Sorry. So any feedback, question, comments on this? Lionel.
Yes, thanks for the presentation. I feel this draft will benefit from mapping the architecture to some business process, such as incident management or network design and so on. Because when I read it, I did not find myself into which part of the framework is related to which part of my day-to-day activities. So it could be interesting to map an incident management process to the proposed architecture to make it more tractable indeed. So that's just a remark.
Okay, sure. Ma'am, thanks for the feedback. We will look into that.
Thanks.
Thank you.
All right, good. So the next one is an experiment on the network anomaly lifecycle draft by Vincenzo.
Hi, folks. Can you hear me okay? Hello?
Yes, we can hear you.
Thanks a lot. Hi, everyone. My name is Vincenzo, Vince. I work for Huawei, and together with Swisscom and Insalion, we've been working on this draft called Network Anomaly Lifecycle. Now, in this presentation, in behalf of the author, I'm presenting some aspects of this draft, and at the same time, I will also discuss about the open source project which is behind this work on the lifecycle that we presented already in the IETF hackathon in the past. There are some aspects that I think we need to go into the details to get some feedback from the working group. Yes. So in terms of the major problem we're trying to solve, you heard already from all the presenters before that anomaly detection is not something that you deploy and it works, but you need continuous improvement. You need to practice postmortem and incorporate learning and feedback into the detection stage. And this is basically what the network anomaly life cycle is about. So based on empirical evidence of the work that we separately did in Huawei and Swisscom, we realized that there are three major stages of this life cycle. The first one is being the detection. So there's a a system or a human being detecting that something is not working as expected in the network. Then there's the validation. So you need to make sure that the detection was done properly, especially if it was an algorithmic detection. You want to somehow understand if the detection algorithm was working as expected, and if not, you want to move into the next phase, which is the refinement. You have to adjust the process by adjusting the information that the process and that the detection process has available to it. And in this work, our major contribution is by saying that this knowledge, this continuous learning, can be codified in the form of labels that substantially describe the symptoms that we see on the network, and that symptoms can be collectively grouped into network anomalies. So in the draft, you will see that there are references to the network anomaly metadata draft as well, which describes somehow the symptom. And then in this draft, there is a full description of the network anomaly data model. So the major contribution is substantially the data model and the state machine for how to use this data model in the different stages of the life cycle. The solution that we see for this problem is substantially the introduction of a new component inside the network anomaly architecture, which we call label store, which substantially is a component which provides some functionalities, in particular the persistency, the upgrade, and the retrieval of the labels, as described before, for multiple actors, and we will see what those actors are, and for all the three, across all the three life cycle stages. In particular, the actors that we see already being in real networks right now are in the detection stage. We see this stage being performed by either network engineers or automatic detectors. And by automatic detectors here, we mean things like rule-based detectors, like the ones that Alex was mentioning before, or SANE, for example, which is something that is already been standardized in the IETF. Or they can be AI machine learning based detectors as well. And for this reason, it is very important that we take into account the validation stage, where the major actors there will be network engineers that manually validating these labels to see how correct they are and adjust them according to any kind of criteria related to how important or how service impacting is a given symptom. And then there's the refinement stage, where the major actors that we foresee are substantially either data scientists, which are substantially trying to improve their own machine learning based detectors, and therefore they have to adjust the labels and provide those labels to the machine learning for retraining and this kind of operations. Or we could also see automatic refiners, systems that substantially take as input the validation labels from network engineers, and they automatically organize the retraining of the machine learning models or the adjustment of the information. For example, they might change the rules or this sort of things. And we see already detectors and refiners are implemented in the industry, and they can be implemented by multiple vendors, by multiple operators. We have our own versions of these things we're working on as well. So it's very important that we start looking at this from an interoperability point of view. So when you have multiple components like detection, refinement, and validation having to cooperate together, you want these things to speak the same language, having a uniform API, which is what we're trying to do with this data model, by the way. And we managed to collect at least 4 major requirements for this API, so that this API has to satisfy. The first being the fact that we need to be semantically consistent from a networking point of view, and this is the main reason why we rely on the semantic metadata draft. Then we also want this model to be human and machine readable, because as we've seen, different actors of different nature are involved in the process. Then, as I mentioned before, we want the different stages and different modules operating in different stages to interoperate between them. And we also want to make sure that the model and the lifecycle allows network experts for validation and adjustments of all the network anomaly labels. So I would say some of the feedback that we might be looking for, and feel free to stop or jump in at any point in time, is if there is any additional requirement that would be worth adding to the list. And by additional requirement, I don't just mean a requirement to the young data model, but also requirement to the life cycle itself. So I will pause at the end of this presentation asking people which operate networks if anyone has any feedback in terms of if this process fits their own internal processes for network incident management or for post-mortem analysis and all these kind of things. This is an experimental draft, so it's an experiment, and the goals that we have defined for these experiments are these three mentioned here. The first one being to define and validate a suitable data model for label exchange across the different actors in different stages. The second one being a validation of this data model across a wide set of scenarios, and the three scenarios we have in mind at this point are human-based detection, validation, and refinement, where everything is done by human beings. Where machine learning based detection is in place, that's the second use case scenario. And the third use case scenario is the automated rule based detection. By the way, the third one is work in progress, and I will mention something about our stage on that. But for the first two, I will likely I would like to go more into the details, and I would like to mention the fact that I've been working on this project called Antagonist, which I presented already in the IETF hackathon in the past. Now here you can find the code. It's an open source piece of software that actually runs. It's a proof of concept. In the link, you can actually find instructions for the deployment and to load some demo data into the system so that you can play a little bit with it. But since it's a POC, feel free to get in touch if you need any help for the deployment. And most of all, feel free to get in touch if you like to test on your own data. So we can probably discuss about how to integrate this thing with, right now it's working with InfluxDB, but we can easily explore integration with other time series data and databases and so forth. So in terms of human-based detection, what the user will see when using this system is basically a set of dashboards in which the user can actually select which metric is supposed to be anomalous and tag graphically on the time series itself what kind of symptom it's basically seeing. And there's a bunch of fields that can be added, and again, these are basically taken from the anomaly metadata draft. And key aspects to be taken into account are the confidence score and the concern score. More in details, the concern score is basically telling the system how badly the symptom is impacting services. And the confidence score is how sure that this is actually impacting or not, because there's a degree of confidence you can have in the process. So the first one helps us to prioritize what symptoms are most important. The second one helps us to understand what symptoms require feedback in validation stage. So if you have a high confidence score at the detection stage, there's probably no point that I'm going to bother the network engineer with some validation on that symptom. But if you have a low confidence score, then this means that this would require a little bit more of exploration and validation on the data. When navigating all these network anomalies, the user will see a list of all the network anomalies that can be explored in details, where you can have all the revisions of all the stages that have been tagged by any of the actors involved in the process. And from this kind of GUI that you have available in the open source system, you can actually add new versions. You can modify existing versions, or you can analyze the details of each single symptom and visualize those symptoms in a charts by, you could actually visualize exactly what metric and what kind of behavior you're experiencing, and this will be visualized using Grafana. And when you deploy the thing, basically this is all Docker based, so it's very easy to deploy. Theoretically, you should be able to do that in a fully automated fashion. Yeah, sorry. For what concerned the machine learning based detection and refinement, we have been doing a little bit of work on this one too. So basically, we have a machine learning based detector, which is kind of a toy machine learning model, although it's fairly complex. It's a neural network. It's an autoencoder, and this has been released as part of the package as well. So if you want to play with it, you can actually do that. And what this does, basically, just to go through the flow very quickly, the first step being the machine learning based detector reading the time series data from the time series DB, and then storing the labels on the label store on Antagonist via REST. In the future, we might actually we are planning to introduce also Apache Kafka at some point as an ingestion mechanism. And then the validation being done via the Antagonist front end and the Grafana dashboard. Basically, the validation step would retrieve the labels, and by adjusting all the query parameters like the mean and the max confidence score, you can actually make sure that the network engineer only validates those symptoms that for which machine learning had low confidence. And then the validated labels, which you can call ground truth, at that point is basically stored again in the label store. And all these steps are using the same data model. And then the final step, which actually the fourth step, is the retrieving of the ground truth. And in the refinement stage, a data scientist can substantially use the new labels to move to step 5 and retrain the machine learning model. And you can see that if you label the data, you can actually see some improvement in the machine learning model over time. In terms of roadmap, what's been done, we have been validating this from a human label management point of view, and we've been validating this with a machine learning-based anomaly detection system. We still have a work in progress of validating this with a rule-based approaches. So we're currently planning to work on phase 4. We started already, and we want to finalize this. We plan to finalize this hopefully by November 24. So for the next IETF, where we should be able to finalize the validation of the POC with SANE as a rule-based anomaly detector. And we're also planning to, as a future step, to integrate this with the Swisscom lab environment. Although, as you can imagine, this process has been designed together with Swisscom, so we're very much sure that the whole life cycle fits within the process the processes. But one very important aspect for us being to get more feedback from other operators as well, just to see if this overall cycle fits with the processes that operators have in place, and if the data model supports use cases, and if this problem is something that anyone would like to cooperate upon. And with this, this is my last slide.
Very good, thank you. So raise your hand if you've got questions. I see Lionel has got a question.
Yeah, hi, thanks, Vincenzo. Regarding the data model, you have this symptoms list. Does that mean that you are focusing on the co-occurrence of many symptoms to be a precondition of some network anomaly?
I think you can, based on the data model, you should be able to have one network anomaly which only includes one symptom. but at the same time, what we've seen in some operational scenarios is that multiple symptoms might occur at the same time, and you will want to collect all of them in order to make sure that the person who has to fix the problem has all the information together. And I'm kind of referring to scenarios where you have multiple symptoms coming from multiple planes, like the control plane, data plane, and you want to make sure that they are aggregated, especially if they are pointing towards the same issue.
Okay, I get it. So my point here is that the data model itself is interesting, but it does not itself encompass all the data that can be shared across operators. It's not self-sufficient if per se. As you say, you delegate the explainability to models and that are aside of the data model. Am I wrong?
I mean, in a way, the exercise here that we've been doing was to validate this as human beings, so without looking at any machine learning model per se. And the reason why we're focusing on symptoms is because we are substantially, so this work is focusing towards the improvement of the detection system. The detection system is the one which has to evaluate if some behavior on the network is somehow concerning or problematic, and therefore you want to. I mean, the symptom is basically the basic. It's the atom of these behaviors. Okay. So a symptom being a behavior seen on a time series data substantially.
Okay, thanks. So if I was to collaborate with you, it will be about making the data model, changing its expressivity to make it more self-sufficient. Well, that's
I will be happy I will be happy to hear from you also offline if you have any more specific feedback to provide. Thanks.
Thanks Vincenzo.
Thank you, Vincenzo. So since you got a little bit of time, Adrian, or any author of the terminology draft, you have a quick message for the working group and an open issue here. So thank you, Adrian. And we cannot hear you.
Try that.
That works.
That's amazing. Only 4 buttons in line to get my mic turned on. So yeah, listening to the last hour and a half of really interesting stuff. I came into this meeting wanting to point up that anomaly is defined in the terminology draft. And that's the main thing I still want to do. And I want to check that the people in this meeting who are working on anomaly are happy with this definition and the little edit which just moves the words around a bit. And I see that I now need to update the reference to point to the adopted anomaly architecture. So my questions would be, is this definition okay? And is this the right reference to be pointing from the terminology out for more detailed discussion?
All right. So any feedback from the working on this? So how do you want to phrase the question, Adrian? Does it work for everybody? And then if you disagree, speak up, or how would you phrase your question? Or just you want to collect feedback?
Yeah, I would say that if there's an immediate comment, that's fine. Otherwise, this should just come back to the mailing list for discussion. and at the same time maybe have a look in the terminology, because we've also got a definition of incident that points out to the incident Yang draft. And I notice that the term symptom is being used a fair bit, and we also have a definition for symptom, which doesn't have a pointer to any other draft. It's just a simple definition. So maybe folks that care could spend a little time looking at the terminology draft and either shout and scream or perhaps just let it go.
Dan?
Yeah. I think we should not let it go. I think we should regroup around what you wrote, Adrian, because I find definitions are really, really important. That's when well written. That's what prevent from people having ongoing and never-ending conversations when people understand properly terminology. So I'm a big fan of what you did, and I'd like to motivate you to not let it go, but also motivate other people here to join and take a stab at the definition that Adrian wrote so far.
Okay, thank you. I think I take that as these definitions should remain in the terminology document, and people should read them carefully and complain if they're not clear and precise and what they want.
All right.
Yeah, very good. Thanks.
Alex?
Yeah, well, actually joining Adrian and Dan, I think that having a draft with all the terminology aggregated, it's useful. So I would support having anomaly, the definition of an anomaly in this draft.
Very good. One quick one, Adrian. So whenever we were referring to the framework, I was checking, so the framework is informational. What about the terminology? It's informational as well. Can you remind me what we do typically with terminology draft? They're on a track, they're informational. And we could take it offline if you want, right?
Yeah. I mean, your mileage will vary from one IESG to the next. I would say that it's informational or a BCP, but probably informational. And while people will need to reference the terminology in order to understand the terms, they don't need to reference the terminology to implement a protocol spec.
Right, because I checked your ops WG OAM, it's BCP. So, okay, let's take it offline, but to be checked.
Yeah.
Thank you, Adrian. So we've got 6 minutes left here. So with Matt, we were chatting on the side on trying to come up with interesting questions that we could ask the working group. So let me quickly read them. Is it worth to document lessons learned, shared out of the valuable, bring your own outage? Credit to Rob and maybe Dan, and share the quick wins. 2, interested to investigate means that would help auto generation of correlation and then help with efficient mitigation. Do we have candidate technical approach? Can data annotation be useful here? Calls for contribution to knowledge graph experiment with focus on anomaly. And the last one is we have so far 2 drafts to plug into the network anomaly detection framework. Does it fulfill the needs of the operator so far? Do we need others? So quick questions that are completely open. Feel free to share your feedback on any of them. Matt, did I ask the question correctly? Is it what you wanted to do?
Yeah, perfectly. Yeah, thanks.
Thank you. So I see Michael in the queue.
Hi, yeah, sorry. I had some network issues earlier. I had I was very interested in Lionel's draft and what he presented. I myself have posted just recently a knowledge graph framework for network operations draft as well. It seems we have somehow collided. Ours went out yesterday. Yours somehow kind of was dropped last week. So there's probably some form of alignment there. I think I would definitely be interested in getting involved in number 3 here and getting involved in the experiments. I do had a question on Lionel's approach, which was really I see there's only 6 minutes, so I'm not sure if we have time. But it was
so maybe you can post it to the mailing list. It's
yes,
always
yeah, maybe that's easier. But for 3, yes, as I say, we have our own draft. It's probably more aligned from a requirements point of view rather than offering any particular solution right now anyway, but it's detailing detailed requirements and maybe an alignment for next steps.
Thank you. Mahesh.
Yeah, and I wanted to thank all the presenters for bringing forth the presentations. I particularly liked Thomas's presentation, fairly detailed. And you mentioned, Thomas, that you wanted to get to the point where you could get to the exact change in config that caused the outage in this particular case. I do have a student, a PhD student that Colin referred me to out of University of Washington that is actually looking at that work. Just remind me, I can send you his reference, and maybe to the chairs, we could have him present his work in the NMOP working group.
Very good. Thank you, Mahesh. Lionel?
Yes, about question number 2, I won't speak on behalf of the working group, but yes, we do have candidate technical approaches. And can data annotation be useful here? Yes, it is. And it can be both learned with a human in the loop or without a human in the loop. We know how to learn remediation procedures and procedural models of what's going on the network. So if I can say yes to the whole question too, but I'm not the only one here.
Thank you for the feedback. Thomas and Michael, sorry, Michael, you're still in the queue, right? You want to remove yourself.
So just a quick one from my side. So yes on 2 and 3. So on 2, our work, which we are currently working on, we are looking very forward on the causality aspect. So basically when multiple connectivity services alert that we are finding the cause why they are alerting at the same time. And that leads also on number 3, on the knowledge graph. I think that will help us to in the causality. Thanks.
Thank you. Vincenzo?
Very, very briefly, I think on number 2, when we speak about data annotation be useful here, I think that's one of the scenarios where the presentation I was giving before can actually be useful. So that might actually sit somewhere with the labeling process and the label generation process. I think.
Thank you. So I see nobody else in the queue. It's exactly the top of the hour. So, Matt, what do you make out of this? On my side, I would like to thank people for the feedback, for participation, for the operators who've been sharing candidly the outages, not always easy. And we'll take into account the 4 questions that we came up with during the meeting, right? And see and take them into account. Anything else on your side, Matt?
Exactly what you said. Thank you all for for sharing this valuable information during the meeting and for the positive spirit of contributing and discussion. That's really appreciated.
Thank you very much.